Welcome to Chapter 5, using fundamental identities. By this time, we should be familiar, and by familiar I mean we have seen these a number of times. Our even odds, our cofunctions, our Pythagoreans. Cofunction identities, understand it's really just one rule, and tangent goes with cotangent, and sine goes with cosine, and cosecant goes with plain old secant. We all know our reciprocals. I'm pretty comfortable with that, and I believe we all know tangent is sine on cosine. Cotangent is, of course, the reciprocal, cosine on sine. For the Pythagoreans, this one we should be pretty familiar with, and I always remember these just by knowing plain old tangent, plain old secant, cotangent, cosecant, and the secant part is always isolated. And we've talked about, and we'll talk about in class, why that one's the isolated one. But to be honest, I don't feel real strongly about memorizing your way through math. These should be right at the tip of our tongue at all times for this chapter. So let's go ahead and take a look. I need to start off by just acknowledging that I was lazy here on copy and paste, and I just used angle T throughout, even when it's angle theta. So of course in number 8, this should really be theta, theta, theta. So we're supposed to use the values, and what I want to really encourage you to do in this section is do it the way they're asking. We want to use we want to use our identities rather than building triangles for this. Yes, I know we could build a triangle in the first quadrant where x is 1 and r is 2 and x is 1, r is 2, y is root 3, and r is 2, and we could do that. But I want to try to stay away from that. This is like trig identity exercises for us. It's just like, it's almost just gymnastics. So cosine is 1/2. If cosine is 1/2, we know that secant's 2. That's the easiest one. Sine is square root of 3 on 2. So secant is 2 on square root of 3, or 2 square root of 3 on 3. And now to get from sine and cosine to tangent, tangent is sine divided by cosine. So this divided by this, the on 2's cancel. I just get square root of 3 on 1. And cotangent is the reciprocal of that, 1 on square root of 3. And there's other ways to navigate around using Pythagoreans, but that's a pretty convenient way for us. So let's take a look at number 10. Tangent. Now, hopefully we're at the stage now where we recognize that thing derationalized, I'm just going to put it up here, is 1 on square root of 3. That's kind of helpful to know. So we'll zoom in a little bit here. They give us cosecant, -2, making sine -1/2. They give us tangent, square root of 3 on 3, which is 1 on square root of 3. The reciprocal of that is square root of 3. And now I'm going to go back to my relationship between sine and cosine and tangent. We could also go with our relationship with sine and cosine here. We could use this, and we could say sine -1/2 squared plus cosine squared equals 1 and solve for cosine. But I'm going to use my tangent relationship, which says tangent 1 on square root of 3 equals sine -1/2 divided by cosine of x. So if I cross multiply here, I get cosine of x equals -1/2 times square root of 3, or cosine is -square root of 3 on 2. And secant, therefore, would be -2 on square root of 3, or -2 square root of 3 on 3. And just started grading last chapter's test. We didn't all rationalize denominators, and that's something I've asked you to do. So in our answers, we're going to have denominators rationalized. Okay, number 12. Hopefully we recognize this as having been the rationalized form of 1 on square root of 26. That's helpful for us. So sine is square root of 26 on 26. Cosecant is the reciprocal of this, or the reciprocal of that, square root of 26. Cotangent is -5, making, that's in the wrong place, that's crazy, -5, making tangent reciprocal of that, negative 1/5. And once again, I'm going to use my relationship between sine, cosine, and tangent here. I know that tangent, negative 1 on 5, is equal to sine. I'm going to make it 1 on square root of 26, all on cosine. Cross multiply here, and I get that should be a colon, not an equal to. I get negative cosine of theta equals 5 on square root of 26. So there's cosine. That's negative cosine, so cosine is negative 5 square root of 26 on 26. And therefore, secant is the reciprocal of cosine. This is cosine. Cosine is negative 5 on square root of 26. So this is negative square root of 26 on 5. Okay, cosecant negative x. Cosecant, like sine, is an odd function. Sine to the left is the opposite of sine to the right. Cosecant to the left is the opposite of cosecant to the right. Therefore, cosecant to the left is the opposite of cosecant to the right. Cosecant to the left is negative 5. Cosecant to the right must be 5, making sine 1/5. Cosine, for whatever reason, they didn't simplify the square root of 24, so we'll just go with that. Square root of 24 on 5, making secant 5 times square root of 24 on 24. Flip and rationalize. Okay, I can't resist this one because this is going to reduce some. So this is 4 times 6, 2 square root of 6 on 24, or 5 square root of 6 on 12. That's why we should have that guy reduced or simplified. Tangent is sine on cosine, 1 on 5, square root of 24 on 5. This just becomes 1 on square root of 24, which is 1 on 2 square root of 6, which is square root of 6 on 2 times 6, 12. Making cotangent want to be 12 on square root of 6, or 12 square root of 6 on 6, or 2 square root of 6. Okay. This one we talked about this last chapter, didn't test on it, but we talked about this cofunction identity, and they just jump right out at you. They're not going to hide these things. Cosine pi on 2 minus x is equal to sine of x. Well, in this case, t, but again, my apologies, I spoke about that earlier. So if cosine of this guy's complement is 3/5, sine is 3/5, making cosecant 5/3. Cosine is 4/5. Sine on cosine, the on 5's cancel, 3/4, and we got made here reciprocal. Sorry about that. Didn't adjust my screen. Secant is 4, cosine is 1/4. Now, tangent is less than 0, and this one they kind of force our hand on this one. They're kind of trying to force our hand on this to draw the triangle, but I'm going to go ahead now and jump and do this with Pythagoreans. I can't jump to sines, cosine, tangent now because I don't know 2 of those. But we do have a rule up above about sines and cosines. It says sine squared, I'm going to call it t, plus cosine squared t equals 1. That's from above. So sine squared of t plus 1/4 squared, 1/16 equals 1. We get sine squared of t is 16/16 minus 1/16, 15/16, or sine of t wants to be plus or minus square root of 15 on square root of 16, 4. That's what sine wants to be. They tell us tangent's negative, so let's consider where we would build the triangle. If secant is positive and tangent is negative, we must be in quadrant 4, And sine is negative here. So negative square root of 15 on 4. Making cosecant negative 4 times square root of 15 on 15. And tangent's easy now. This on this, the on 4's cancel, we get negative square root of 15. Oops. Cotangent wants to be 1 on negative square root of 15 or negative square root of 15 on 15. Okay. Now we're going to get into some simplifying. This becomes hugely important in calculus. Match the trigonometric expression with its simplified form. So 22 should simplify to be one of these. And now is where we have all sorts of little trigonometric rules that we might be using. And we're going to be specializing in this for quite some time. But you're going to be just learning different tricks, different tools in the toolbox. And one of those I would do, if we have two different trig functions, I try to determine, do they live together in a Pythagorean relationship? Well, tangent is Pythagorean with secant, and cosecant's Pythagorean with cotangent. So I like these guys together, and I like sine and cosine together, but I don't like tangent and cosecant together. So I'm going to migrate to sines and cosines. And tangent is sine of x. Tangent of x is sine of x on cosine of x. And cosecant of x is 1 on sine of x. Well, that's convenient. That equals sines cancel 1 on cosine of x, which is not a choice up here. But cosine in reciprocal form, this is secant. Secant of x. So this is A. Okay, another trick. Anytime we have a trig function squared, I'm going to consider its Pythagorean. And if I have it plus or minus 1 or something along that line, then I'm definitely going to be considering Pythagorean. So let's take a look at our sine squared plus our sine squared cosine squared. Is it easy to manipulate or convenient? Can we manipulate this to be 1 minus cosine squared? Sure, if I just subtracted cosine squared, sine squared would equal 1 minus cosine squared. So this is a really nice, convenient. If this was 1 plus cosine squared, it wouldn't be as useful, but this is just sine squared of x. I think I'll take this and turn this one into 1 on sine of x. One of the best things we can do, if we can get everything into just one trig function, then it's just plain old algebra, where we treat sine of x like a variable. So sine cancels a sine, we just get sine of x, and this is f. Okay, and remember when I said on the back page, the cofunction rules, they don't disguise them. Sine of 90 degrees or pi on 2 minus x is cosine of x. Cosine of 90 degrees or pi minus 2 minus x is sine of x. And cosine of an angle on sine of an angle is cotangent of the angle. This is cotangent of x or c. Okay, and similar. These are so important. They've got a couple sections of these. Cosecant squared. So maybe Pythagorean. I love cosines and secants together because cosines and secants. Oh, because they're reciprocals. Excuse me, lost my train of thought there. So they're reciprocals. However, so I might be tempted to distribute this, but I might be tempted to say, can I get a secant squared minus 1 here? Secant squared, if I subtracted 1, would be tangent squared. Maybe that's useful. Cosine squared of x times tangent squared of x. Let's convert this to sines and cosines. I get cosine squared of x times sine squared of x on cosine squared of x is sine squared of x. Now, I mentioned maybe we should distribute because we have this cosines and secants are reciprocals. Let's see what would happen there. Draw a line. If I distribute this, cosine times secant, or cosine squared times secant squared, is just 1. They're reciprocals. 1 minus cosine squared of x. but 1 minus cosine squared of an angle is sine squared of the angle. So that's one of the nice things about, well, it's intimidating, but it's liberating at the same time, because so often you've been taught in algebra, do this first, do this second, do this third, solve for x. We're going to do these steps in this order. Now all of a sudden you got some freedom. It's much more like a chess game where you're going to kind of try to think ahead a move or two. What might be a good idea? But I liked cosines and secants. They're reciprocals, but I also liked that this was a Pythagorean and turned into plain old tangent. Okay, cotangents and secants do not live together in a Pythagorean. So much like this problem, I'm going to go to sines and cosines. Cosine of x on sine of x, there's cotangent, times secant, 1 on cosine of x. Cosines cancel, 1 on sine of x simplifies to cosecant x. Let's take a look. We've got to go back to this problem. This is c, of course, then. Cosecant x, this is e. And once again, there we are. Cofunction rule. Cosine squared of this angle is sine squared of plain old x on cosine of x. So we look and see, and we're like, oh, I don't have anything up here that looks like that. So what could we do? I mentioned up here, the best thing we can do is if we can get everything in just terms of one trig function, it's probably worth doing. So this guy, sine squared, is equal to 1 minus cosine squared. So this is 1 minus cosine squared of x on cosine of x, which could be written as 1 on cosine of x minus cosine squared of x on cosine of x. Well, that's nice. 1 divided by cosine, that is secant of x. Secant of x minus cosine of x, is that a choice? We don't have a choice for that. So did we come up with something along the way that might work well for us here? This is one of the interesting things, because sometimes simplified is in the eye of the beholder. So this could be, let's see, we could make this, I'm going to come back to this one right here. Promise you, I'll come back to 32. I want to get some other things done, but I don't believe that I've made an error there. Yep, I'm going to come back to it. Apologies on that one. Let's continue on here. I believe everything here is right. Simplified sometimes, as I mentioned, is in the eye of the beholder. So we're going to work toward one of these shortly. Okay, in exercise 33-44, use fundamental identities to simplify the expression. Use a table feature. So cosine times tangent. They don't live together in a Pythagorean, so I'm going to go cosine of beta times, I'm going to go to sines and cosines. Sine of beta on cosine of beta, and that, of course, is sine of beta. 1 plus tangent squared, that looks Pythagorean to me. Yep, if it was 1 minus tangent squared, it wouldn't be as useful. 1 plus tangent squared is secant squared. So cosine of x times secant squared of x. Love cosine and secant together. Reciprocals. Cosine of x times 1 on cosine squared of x is 1 on cosine of x, which is plain old secant of x. Okay, 38, secant on cosecant. Well, it sounds good, but secant and cosecant aren't reciprocals. They don't live together in a Pythagorean, so I'm going to go sines and cosines and create a bit of a mess. This is, this is 1 on cosine of x divided by 1 on sine of x. And a fraction divided by a fraction is the first fraction times the reciprocal of the second fraction, and now we're getting somewhere. Sine of x on cosine of x. The which is tangent of x. Hopefully we're catching on to these. We see squareds. Think Pythagorean, especially when there's a plus or minus 1, something along that line with it. 1 plus tangent squared is secant squared. So this is secant squared of theta on secant squared of theta, or just 1. Cotangent pi on 2 minus x sticks out like a sore thumb. That is tangent of x times cosine of x. And that sounds really familiar. Cosine tangent are not reciprocals. They don't live together in a Pythagorean. Let's go sines and cosines. Sine of x on cosine of x times cosine of x, if you like, on 1. Cancel, cancel. Sine of x. What are we thinking about? Pythagorean. Let's take a look. Ooh, cotangent squared plus 1 is cosecant squared. This is 1 on cosecant squared of x, which is certainly simplified from there, but even better would be if there was no division. The reciprocal of cosecant is sine. So this is sine squared of x. Okay, I'm going to continue on. Factor the expression and use fundamental identities to simplify. Okay, I guess they're telling me what to do here. Factor, I get secant squared of x, I can factor out, and I'm left with tangent squared of x plus 1. Tangent squared plus 1, sure enough, is secant squared. So this is secant squared of x times secant squared of x, or secant to the 4th of x, and I don't think we're going to get any more simplified than that. 48, factor. How the heck do we factor this thing? Well, I bet if it said x squared minus 9, you'd all know how to factor this. X plus 3x minus 3. This is a perfect square minus a perfect square. So this is cosecant x plus 1 times cosecant x minus 1. And we couldn't reduce cosecants before, although somebody's going to try, I'm afraid, because they're terms. Now I've got a factor of cosecant x minus 1 and a factor of cosecant x minus 1, and we're left with cosecant x plus 1. Okay. Factor, you've heard me say this a lot of times. If there's 3 terms, I'm hoping it's quadratic. And this is quadratic. On sine squared. So maybe it factors into sine squared of x and sine squared of x, because this times this gives me sine to the 4th x. Factors of 1 that add up to negative 2, negative 1 and negative 1. And that's factored. We can check it. Sine to the 4th, negative sine squared x minus sine squared x minus 2 sine squared x and a plus 1. What are we thinking here? Is it Pythagorean? Sine squared minus 1. Sine squared, careful here, I could get a minus 1 with it, and I'd have to subtract the cosine squared to the other side. Sine squared minus 1 is equal to negative cosine squared. So this is negative cosine squared x times negative cosine squared x, which becomes negative times negative positive cosine to the 4th x. Factor difference of perfect squares. So this becomes secant squared x plus tangent squared x times secant squared x minus tangent squared x. What are we thinking about? Pythagorean, secant and tangent? Yep, I can get a secant squared minus tangent squared by subtracting, and that's just 1. I can get that. So secant squared minus tangent, let's get to that in a second. Secant squared x plus tangent squared x. Secant squared minus tangent squared is just 1. And that, I would suggest, we could probably make an argument that that's simplified. However, we could also say secant squared is 1 plus tangent squared. We could also make this 1 plus tangent squared x plus tangent squared x, or 1 plus 2 tangent squared x. And I would suggest perhaps there's a good argument that that's more simplified than that. I'm not certain what the back of the book does. Okay, we see this. The best thing about this is it's all secants. The worst thing is how in the world do we factor that? Don't get caught up in the trigonometry. Just take a look. If there's 4 terms, how do we factor? Hopefully everybody at home is at least in their head saying by grouping. Let's see. I'm going to factor secant squared x out of the first 2. And I get a secant x minus 1. I would love to be able to get another secant x minus 1 here. Can I? If I factor out minus 1, I can. So now I factor this out, secant x minus 1, and I get a secant squared x minus 1. Sounds Pythagorean. It is. Secant x minus 1, all of it, times tangent squared x. Well, does anything good happen here from this point? I mean, I could turn this back into secants, but I'm just heading up there. So I did get some, I would say this is probably maybe a little more simplified than that. Now, sine, if we look at if we look at sines and cosines route, I'm not certain this is going to help us much, but let's take a look. This could be sine squared on cosine squared of x. And this is 1 on cosine of x minus 1. I don't get any good canceling when I distribute this through, so I'm going to suggest that may be about as good as we can do here. My pledge to you is when we get something, if I give you a simplified problem, I want it to be something that simplifies and there's going to be no debate what the simplest form is, like this. There's no way we're going to simplify beyond that or that or that. And I would suggest even this. But this one is like there's a lot of mixing around of things we could do. I'm gonna try to have simplified problems for you on quizzes and tests where things simplify, and when you get to it, it's going to be, oh yeah, that's got to be it. Okay. Perform the multiplication and use the fundamental identities to simplify. So this is foiling. So we get 1 plus 2 tangents of x plus tangent squared of x. And okay, what can we do here to simplify? And this is debatable. I do have a tangent squared with a plus 1, and there's a tangent squared with a plus 1. So this and this could simplify to be secant squared x plus 2 tangent of x. Is that really simplified? We have 2 different trig functions now, but we have a binomial instead of a trinomial, and that's one of those simplifies in the eye of the beholder a little bit. Let's take a look at this. Distributing, foiling, I get 25. I get plus 25 sine x minus 25 sine x, and I get minus 25 sine squared x. All right, well, the 25 is jumping out at me. Let's go 25 times 1 minus sine squared x. And what are we thinking? Pythagorean? Can I get a 1 minus sine squared? Sure enough, that's cosine squared. So this is 25 cosine squared x, and that's a simplified problem that I would want to put on a quiz or test. Once we get to this point, there's no way in the world we're getting that simplified. We could change its form, but not simplified. All right, I'm going to wrap this one up. As you can see, this is a long section. We'll do this over a couple of days. Perform the addition or subtraction. Well, how do we do that? Well, how would we perform this subtraction? 1/3 plus 2/5. We'd change that to on 15. Multiply by 5 over 5, plus multiply by 3 over 3, and we get 11/15. So we need common denominators. My least common denominator here has to have a factor of secant x plus 1 and has to have a factor of secant x minus 1. So this fraction had to be multiplied by secant x minus 1 on secant x minus 1. So 1 times that is secant x minus 1. So 1 times that. Minus, this minus 1 had to be multiplied by secant x plus 1 on secant x plus 1. And hopefully you spot the danger here that some people might have. We got to make sure to distribute that negative. So let's see, in the numerator we get secant x minus 1 minus secant x minus 1 all on, this, believe it or not, is actually going to be beneficial to FOIL out. Secant squared x minus the secant x plus the secant x minus 1. And in the numerator, we get negative 2. In the denominator, we've got this. Pythagorean. Let's see, secant squared minus 1. Secant squared minus 1 is tangent squared. And that's awesome, and that's very simplified compared to what we started with, but we can still do better. Because the reciprocal of tangent is cotangent, this could be written as negative 2 cotangent squared of x. Okay, so 62, we need common denominators. Our least common denominator needs a factor of 1 plus sine of x, which means this first term, tangent of x, had to be multiplied by 1 plus sine of x. The second term was fine. It was already on 1 plus sine. So here we go. We get tangent of x plus tangent of x times sine of x plus cosine of x all on 1 plus sine of x. All right, we got 3 different trig functions now. I'm going to go to sines and cosines and hope something good happens. Sine of x on cosine of x plus sine of x on cosine of x times sine of x plus cosine of x all on 1 plus sine of x. Plus sine of x. Now, we've really created a mess here. I'm going to actually refer to this mathematically as a mess. It's when we create compound fractions with trigonometric functions in them. I'm going to multiply the top and the bottom of this thing by cosine of x. And when I do that, I can do that because I'm multiplying by 1. The cosine cancels, I get sine of x. The cosine cancels, I get plus sine squared of x. The cosine doesn't cancel, I get plus cosine squared of x, all on cosine of x times 1 plus sine of x. I want you to take a good look at that. That's a mess right now. It's still kind of messy. At least it's not compound fractions, but there's some real goodness going on there. Do we see it? Sine squared plus cosine squared is 1. So this is, man, I'm really painting myself into a corner here. This is sine of x plus 1 on cosine of x times sine of x plus 1. Those cancel. I get 1 on cosine of x, which is secant of x. Well, there's a lot going on that problem. Okay, I need common denominators here. I love secants and tangents together. They live together in a Pythagorean. So my least common denominator here, I need a factor of 1 plus secant of x. I need a factor of tangent of x, which means this tangent of x, this term had to be multiplied by tangent on tangent, tangent squared x. Plus this had to be multiplied by 1 plus secant on 1 plus secant. 1 plus secant of x times 1 plus secant of x. Well, let's FOIL and hope something good happens here. Tangent squared of x plus FOILed 1 plus 2 secants of x plus secant squared of x. That's kind of workable. all on. I'm going to leave this and hope maybe something might cancel. So I'm not going to distribute this yet. All right. This tangent squared could be turned into secants. Or this secant squared could be turned into tangents. But I think I'd rather have the whole top be secants. So let's see. Tangent squared of x. Oh, and there's even a plus 1 with it. Tangent squared of x plus 1 can be turned into secant squared. So I get secant squared of x in place of this, plus 2 secant of x's, plus another secant squared x, all on 1 plus secant. I'm still holding out hope that maybe I can reduce the denominator. And let's see, that's 2 of these secant squareds, all on 1 plus secant x times tangent x. If I factor out a 2 and a secant, well, something good did happen. 2 secant x, I'm left with a secant of x plus 1 on a 1 plus secant of x times tangent of x. And we're looking pretty good right there. And now I'm going to bring that down just to make certain that I can't simplify things further by going to sines and cosines now. So I'm going to jump down to the bottom of the page and write what I have here. 2 secant of x on tangent of x. Let's see, that's 2 on cosine of x over sine of x on cosine of x, which is equal to 2 on cosine of x times, flip it, cosine of x on sine of x. Cosines cancel. 2 on sine, holy cow, 2 on sine is 2 cosecant of x. Apologize for running out of room there. Didn't pre-do this problem, but perhaps you can find a quicker way to there. But we're not going to be able to simplify beyond that, 2 cosecant x. All right, rewrite the expression so that it is not in fractional form. So I want to get rid of cotangent. I'm going to go to sines and cosines first here. Even though these live together in a Pythagorean, there is no, and maybe I want to come back to that. But even though they live in a Pythagorean, I'm going to go to sines and cosines and see if that cleans things up here. So this is 1 on sine of y over cosine of y on sine of y, which is equal to 1 on sine of y times flip and multiply sine of y on cosine of y. Sines cancel, 1 on cosine of y, but it's still a fraction, but that is equal to its reciprocal function, secant y. Okay, tangents live together in a Pythagorean with secant, unfortunately, not cosecant. I am kind of thinking along the lines of Pythagorean, but I'm also kind of thinking along the lines of sines and cosines. I think I'm going to go sines and cosines here. So this is, tangent is sine squared of x on cosine squared of x, all over cosecant is 1 on sine of x plus 1. Tangents don't live together with cosecant in a Pythagorean. And now I created that mess, and here's how I would clean it. This is a big step for us. Out of this term, and this term, the least common denominator, we need a cosine squared, and we need a sine. This is what I call just cleaning the mess. I'm multiplying by 1. Cosine squareds cancel. I get sine cubed x, all on. When I distribute this to here, sine cancels. I get cosine squared x plus cosine squared x sine of x. Any payoff there? Well, I could factor out, I think I'm going down a bad road here. Sine cubed x on, I can factor out a cosine squared. Cosine squared x times 1 plus sine of x I could turn this into sines because it's a cosine squared. This guy can turn into sines. Hoping something good's about to happen here. Let's see. Cosine squared is 1 minus sine squared. 1 minus sine. So this is sine cubed x on 1 minus sine squared x times 1 plus sine of x. Is there going to be any payoff in superfoiling this out? Because I'm running out of room here, and I think I might have headed down a wrong road, I'm going to give this a shot, but I've got one other problem that I've got to come back and add a video to because I'm writing in pen. Bad mistake for a mathematician. But let's see where we get. Sine cubed x. If I superfoil this, I get 1 plus sine of x minus sine squared of x. And I get a minus sine cubed of x. Okay, we're going to come back. In fact, I'm going to go with this one right now and show you what we maybe should have thought about doing here. Okay, what we could have done was take a look at this and think about anytime I have a plus 1 or minus 1, it's tempting to start thinking Pythagorean, but I wish this was squared. If I would take this tangent squared of x on cosecant x plus 1, sometimes using conjugates is a good idea. Let's see what happens if I multiply this by conjugate. Cosecant x minus 1 on cosecant x minus 1. In the denominator, I'm not going to distribute the numerator yet. I may later. But good things happen in the denominator. I get cosecant x squared, cosecant squared x, minus cosecant plus cosecant minus 1. Now, anything good happen there? Well, Pythagorean maybe. Cosecant squared minus 1 is cotangent squared. Cosecant squared minus 1 is cotangent squared. So this is tangent squared x times cosecant x minus 1 all on cotangent squared x. The reciprocal of that is tangent squared, so this becomes tangent to the fourth x times cosecant x minus 1. Now, I would love to bluff you right here and say that I did this just to prove a point to you, but I did this because I thought it might be a viable avenue for us. That's the thing about trigonometry. A lot of times when we're simplifying or working on identities, you've got some choices. And like I said, much like chess, you want to kind of look ahead and see what good can happen. Well, I got to a point here where as far as putting it in not fractional form, didn't seem like things were, in fact, once I got to here, I knew we were in trouble. Didn't seem to be working out very well. So I went ahead and said, let's go back to the drawing board here and let's try something different. Okay, with that said, I'm going to go ahead and just jump right in. Tangents and secants live together in a Pythagorean. I wish they were squared. I'm going to go with conjugates right away here. Tangent of x minus secant x on tangent x minus secant x gives me 5. I'm going to leave this as tangent x minus secant x over tangent squared x minus tangent secant plus tangent secant minus secant squared x. Well, this secant squared could get turned into tangents. Is that beneficial? Let's take a look. Wrong form. Secant squared is equal to 1 plus tangent squared. See if you can spot this error. Secant squared is 1 plus tangent squared. So this is tangent squared minus secant squared is 1 plus tangent squared. Did you spot the error? It's one I talk about all the time. Here we're subtracting secant squared, so down here we're subtracting that same value. So this becomes 5 tangent of x minus 5 secant of x all on, take a look at this. We're going to get a minus 1, but I'm going to have a tangent squared minus a tangent squared. So that's it. And then get rid of the -1, multiply top and bottom by -1, and I get -5 tangent of x plus 5 secant of x. Okay, all I owe you, I got one problem. I'm going to come back, make a short little video because I got fifth hour's about to start, and I got to get things prepped for them. Here's our assignment from this section. Again, we'll be covering this over 2 days. And good luck. Come in, ask questions as needed. They're a very, very important section for us.